Good afternoon. It's time to start the Modern Trends in Physics Research seminar. Today's speaker is Dr. Tomasz Grzywalski. Dr. Tomasz Grzywalski is an engineer and researcher working at the intersection of artificial intelligence and sound analysis. He earned his master's degree in electronic engineering from Poznań University of Technology and has spent over 15 years in industry working in roles ranging from software and computer vision engineering to audio machine learning. He has worked both in startups and large companies, including Samsung Electronics, at an early stage startup, iChap Technology. He led the development of image recognition systems that were later used in commercial products and by global brands. Since 2017, Tomasz has been with StethoMe, a medtech startup, where he led the development of an AI-based medical device for analyzing lung and heart sound, the first solution of this kind to receive CE certification. The technology has been used by thousands of patients across Europe and has been clinically validated by international research teams. In parallel with his industry work, Tomasz pursued academic research. In 2022, he joined the WAVE research group at the Department of Information Technology of Ghent University. In June 2025, he defended his PhD under the supervision of Professor Dick Botterdoren and co-supervision of Professor Jędrzej Kociński. His doctoral research presented in the dissertation entitled Advanced Techniques for Insulating Sounds of Interest in AI Listening involved close collaboration between academic and industry, including participation in projects funded by European Union and international organizations. He is the author of or co-author of over 20 scientific publications and a recipient of several awards for both research and commercial innovation. The title of presentation is in the screen, so please, the floor is yours.
Thank you. Thank you for the introduction. Thank you for inviting me to this seminar. The title of my presentation is Learning to Listen Again, Cycles of Understanding in Artificial Intelligence. And this presentation is based on my research that was published in my dissertation. I will start with a short introduction to paint a broad picture of what I will be talking about. We use our hearing every day to notice danger, enjoy music, follow conversation, or just stay aware of our surroundings. Artificial intelligence teaches computer to listen using microphones and to analyze sounds to understand spoken commands, notice important sounds like alarms or cries for help, focus on what matters, or make sense of busy sound environments. Artificial listening is mainly based on artificial neural networks. They were first introduced in the 50s, and they are inspired by how our brains work. They are made up of artificial neurons, which are very simple models of real brain cells. While they don't function as real brain cells, they are very good at finding patterns in the data, including sound. Artificial neural networks don't start out smart. They learn from examples, just like humans. At first, artificial neural networks produce random answers, but by being exposed to training data, actual examples, they start to recognize the patterns that we want them to recognize. This is called supervised learning. The most important part of artificial neural network is its architecture. It defines how many neurons there are in the neural network and how they are connected. And by training a neural network, the connections between neurons become stronger, and therefore the network learns how to recognize a pattern. With the right architecture and enough training, artificial neural network can do complex tasks like sound recognition, detection, and separation of sounds. Typically, neurons in artificial neural network are connected in a straightforward manner. So they are organized in layers, and the layers form a cascade so that each neuron receives information from neurons from the previous layer, and the information propagates through the neural network in a straightforward manner, using one pass from the input to the output. And this is called one-shot data interpretation. And this is basically how most neural network used today for sound recognition work. Despite enormous progress that has been made and extra super good quality of algorithms, understanding complex audio environments is still a very challenging task, even for big neural networks. So it could be said that we already figured out how to represent brain on a very small scale, on the scale of neurons. But there is still something missing. We are still looking into how the more general flow of information within the brain happens and how we can leverage that information to make the models work even better. So the central question that I've been asking in my dissertation, and also that is being asked by many researchers all over the world, is can we be inspired by how the brain works on a more general level and use that to improve the architectures of neural networks? My contributions that were presented in my dissertation used three models that were discovered and explained by neuroscientists. But for this presentation, I selected only one because we have limited time and I wanted to go a little bit more into details. So these three frameworks that I've been working in my dissertation is cognitive cycle theory, dual process framework, and long-range neural connections. And from these three, I selected only the first one, the cognitive cycle theory, which will be going into details in my presentation. Okay, so a couple of words about cognitive cycle theory. So I previously said that current neural networks are still working like a one-shot process. So basically, they have one pass of information through the neurons, and they make a prediction. Well, the human cognition doesn't work that way. The human cognition works in cycles, and the cycles repeat themselves, and they also cascade and trigger other cycles. And usually when we are solving a complex task, we need multiple of those cycles in order to be able to comprehend and make a prediction, make a decision. And the cycle usually involves three crucial steps: prediction, comprehension, and decision making. And in my research, I implemented these ideas in two different ways in artificial neural networks. I proposed parallel cyclic processing of neural networks and sequential cyclic processing. And in the remaining part of my presentation, I will be describing two big projects. In the first one, I used parallel cyclic processing to improve the performance of neural networks, and the other one will be focusing on sequential cyclic processing. Okay, so the first of the two big chapters is related to chickens, which is a little bit funny because usually people don't think that chickens is something that should be a subject of very serious research, but actually I hope I will convince you that this is not the case and we can learn a lot and do very interesting research around chickens. But before we go into details, I want to explain why chickens? What's so interesting, and why should we even try to understand what the chickens are saying to each other? Okay, so it's not just curiosity, because it's a real-life problem that we were trying to solve. And the problem is that we are breeding a lot of chickens because we eat chickens every day, and this is like major part of our diet. Okay, and breeding a lot of chickens causes a lot of problems, and still those large stables of chickens need to be manually overseen by veterinary experts. So there is a big investments to try to reduce the need for manual oversight of these stables. And one of the solutions that is being seen as very, very promising is to use acoustic analysis. So basically the idea is that we want to take these huge poultry farms and install microphones over them in a regular grid, capture sounds, vocalizations that the chickens are making, automatically analyze them, and figure out whether they are healthy or not. If they are doing well, everything is fine, or if they may be stressed, they start picking each other, maybe they are sick, start coughing, etc., etc. And all that can be done just by analyzing their vocalizations, checking patterns, and seeing if they match the pattern of a healthy chicken. Okay? Okay, so what do we know already about the types of sounds that the chickens are making? The literature so far distinguished 4 basic types of vocalizations that the chickens are making. The first one is distress calls, as can be seen here. Oops, sorry. Here at the top. And yeah, as the name suggests, these sounds are made by the chickens when they are stressed, when they feel that they are in danger. So if they are emitting these types of sounds, we should be worried as well and check what's wrong with them. On the other hand, short peeps are very similar sounds. They have very similar acoustic properties, but they are lower in energy. And instead, they represent high activity curiosity of chickens, which is absolutely normal and something that we would like to see in healthy chickens. Chickens also sometimes make pleasure notes, which is super good sounds. They are very happy and exploring, etc. And when they are lonely or not very active, they are producing warbles, which are most complex in terms of like spectral characteristics, because they have ascending and descending frequencies. Okay, so we started the project by first gathering a big data set. Of course, we are dealing with neural networks, so we need big data sets to train our models. Because publicly available, public data sets are not really available, we created our own data set by recording a big, well, not so big, but relatively big stable of chickens and recording them throughout their whole life cycle and semi-manually selecting those sounds to train our model. And the model that I initially proposed is a deep convolutional neural network that consists of 11 layers of neurons. And the network processes a spectrogram, which is, as you might know, a time frequency representation of an input signal. Because our data set wasn't that big, it was relatively big. It contained over 2,500 examples, but from the point of view of modern neural networks, this is not a very big number. So we started improving this neural network by pre-training it on a related data set. And because my invention is highly related to the pre-training step, I wanted to shortly describe and give you an idea what pre-training is and why we do it. Okay, so now we are dealing with a problem of training a neural network on a data set that is relatively small, but we want to leverage the fact that we have a related data set that is much bigger. In this example that I'm showing you here, we are for a moment forgetting about sound and focusing on image. So let's say we have a very big data set of cars, but what we actually want to recognize are planes. But we have a big data set of cars. So we start training our neural network to recognize cars, and different layers of neurons become adept at detecting features of different complexity. So the initial layers of the neural network detect very simple features like horizontal, vertical lines or blobs of colors, etc., etc. As we move deeper into the network, the features become more sensitive to higher level features, like we have cars, we have curves, etc., like bigger objects in the image. And if we move even further, we have even more detailed pieces of a car that the neurons are becoming sensitive to. And based on these predictions, we can detect whether this is a car or not. Okay, so now we have trained our model to detect cars, but we want to detect planes. So now we need to fine-tune the network. So now we are using our small data set of planes to make it detect planes, but we want to use the features that the model already learned. And one way of using those features that were already learned is to freeze them, which means that during fine-tuning, we will not be changing them at all. Basically, we're building a new classifier that is based on features that were learned on a different data set. So now the question remains, which features will be good to detect planes? Obviously, the very basic features, like these features here, will be useful for detecting plane because it consists of those different lines and blobs, and etc., etc. But what about these features? Will the wheel or those curves will be useful for detecting planes? Some of them might be, some of them might be not. But these features are already probably too specific for cars, and they will be not very useful to detect planes. So there are some layers of the new of features that we would like to retain because they contain useful features that we might use to detect planes, and the other ones should be rebuilt because they are not very useful. And this usually requires us to make a decision which layers of the network should be frozen and which should be fine-tuned. And we use exactly the same approach to detect broiler sounds. And I was investigating how many layers I should freeze in the network. And on this plot, you can see what was the performance of the broiler vocalization recognizer depending on the number of layers that I have frozen. And as you can see, between 0 and 4 layers gave a very good performance. And when we were freezing even more layers, the performance started dropping, which is what we would expect, because these features in the layers above 5, let's say, were too specific for the data set that I use for pre-training. So they were not specific enough for broiler sounds. But I had to make a decision, but I don't like to make decisions. So I decided that I want to build a model where I wouldn't have to make that decision at all. And the model that I propose is a branch model, when basically I first do a pre-training. I train one branch on my pre-training data set, and then I create 5 copies, and within each copy, there's a different number of frozen layers. And so I create this meta model that consists of those different branches, and then this model is trained to make the predictions about broiler sounds. And on one hand, this is kind of an application of cyclic processing, because each branch in this model is actually making an independent prediction about the sounds. And the important advantage of this model is that the model can decide itself which branch is better for detecting which types of sounds. Because there might be some interesting examples in the pre-training data set, and I might already have good features to detect some of the sounds, but other sounds might require rebuilding of the whole stack of features for me to be able to detect this kind of sound. And when this model was tested, like dissected branch by branch after training, it was actually found that the model showed a specialization. So indeed, we could see that the distress calls, which are the most obvious sounds and most easy to detect, were detected by the branch that had the most layers frozen, because the features were already there, learned during the pre-training. But to distinguish them from short peeps, which are very similar but require much more precise features or specific features, these required retraining of all the layers, and therefore the branch that had the fewest layers frozen was more sensitive to short peeps. Eventually, this approach allowed us to improve the performance of the recognizer by around 3 percentage points on average, but it was over 5% for the short peeps alone. The gain was statistically significant, so we repeated these experiments multiple times and found out that this architecture really improves the detection. What is important, we also tested bigger models. So my branch model is much bigger than the single branch model, but so the question arose if the performance is bigger, maybe just because I'm using a bigger model, and the answer is no. It's not just the size of the model, it's just smarter and it can do more things than a regular model. The disadvantage of this approach is that I have a bigger model, so it's slower. And this model was intended to be deployed on an edge device, and on an edge device it ran 2 times slower. So it's still an open question whether these additional 3 percentage points are justified for additional computational cost. But the research itself was so interesting that it sparked a lot of follow-up research. So eventually we published 3 conference presentations, and we've written 4 articles, from which 3 are already published. And in the next couple of slides, I would like to show you in a very short way what we found in those follow-up studies. This is not like directly related to the deep neural networks. This is the way that we used this recognizer as a tool to learn something about the chickens. Okay, so first of all, we were checking how these vocalizations change in chickens over time, so as the chickens get older and older. And so this was a first very interesting observation. So we have different colors to show different types of vocalizations, and this axis is the age of a chicken. So as you can see, the blue color, initially chickens, young chickens show quite a lot of pleasure notes, but they fade away quite quickly. They are replaced by short peeps, which is still very good. So for some time they are making most of short peeps, but eventually they start making a lot of distress calls, even when they're fine. So this was quite unexpected, but because we didn't expect so many distress calls in healthy chickens. And what was even more interesting, we had a fifth class when we put all the sounds that we couldn't recognize. So we found a lot of different vocalizations that didn't belong to any of those 4 classes, and we put them in a 5th class, like an umbrella, everything else that we couldn't recognize. And as you can see, these sounds appear more and more as the chickens get older. And the conclusion was that probably we don't know everything about the vocabulary of the chickens. We know all of their vocabulary when they are young, but when they are getting older, their repertoire of sounds becomes wider, and they probably start making new kinds of vocalizations that we don't understand yet. So we followed up on this, and okay, this is also a daily pattern. Probably not so very important, but we could also see a very clear daily pattern of the vocalizations, and especially in the night when there is dark, the chickens are quiet, they are not making any sound, they are sleeping. So this is like a sanity check maybe, that it also produces reasonable results. But we were very interested in finding those new types of vocalizations that we didn't understand yet. And to do that, we employed advanced clustering based on deep features. So basically, each color on this map represents like a constellation of very similar sounds, and we were trying to identify different new types of vocalizations. And indeed, we found 10 classes of new vocalizations that they are completely different from the 4 that we presented before. But we still haven't assigned any meaning to them. So we don't know exactly when the chickens are making those sounds. We just published how they sound, what's the acoustical characteristics of those sounds. And now there are follow-up studies which try to determine when the chickens are making these types of sounds. And of course, something that the poultry industry is interested in the most is trying to figure out how to detect when the chickens are sick, because this is the biggest concern. So on one hand, we are checking how the pattern of vocalizations changes when the chickens are sick. And in this plot on the left here, this is a pattern of vocalizations day by day, hour by hour, for chickens that were infected with coccidiosis. And as you can see, the chickens are making exceptionally lot of distress calls quite early. But then as they get sicker and sicker, they become quiet. So all of this information can be actually used to detect when the chickens become sick in this table. And also we noticed that they produce different types of vocalizations. So we are now repeating the clustering process in an attempt to find these new types of vocalizations. This is probably some types of sounds, maybe not vocalizations itself, maybe it's like sneezing or coughing, like a very specific way that the chickens are coughing. But there are definitely forming these clusters of sounds, and we should be able to identify them and therefore be able to detect when the chickens are sick, which would be a huge, huge deal for the poultry industry, not only in Belgium, but all over the world. Okay, so this was about broiler chicken vocalizations and how I use the parallel cyclic processing to improve the performance of the model. The second part of my presentation will be dealing with humans and speech enhancement. So it's a different application of audio processing. And in this case, this is a very classical signal processing task. So we are giving a single recording of a human speech that is polluted to some extent with the background noise. And our task is just to completely remove the background noise so that the speech becomes more intelligible and easier to understand by everybody. So, of course, the potential applications of such technologies are well known and very broad. And also, there are a lot of algorithms that were proposed to solve this kind of problem. In this case, we didn't build our own data sets because there are a lot of data sets available on the internet. So we used publicly available data sets of clean speech utterances and different sources of noise. From these, we built mixtures when we were mixing clean speech with background noise to create those noisy mixtures and training the deep neural network model to entangle this and suppress all the background just to leave the clean speech in the signal. And in order to do that, we once again used different types of deep neural networks. On the input to the network, we used power spectrogram. In this case, the best performing, well, let's say state-of-the-art right now, is to predict complex ideal ratio mask, which is a complex matrix that we multiply by the input spectrogram in order to suppress all the noise and just leave the clean speech. So it's not like completely resynthesize the speech, but instead producing a mask that says which part of the spectrogram actually contains speech, which contain the noise, and just suppressing the noise to leave only the clean speech. Also, the evaluation metrics that we use in this project are quite standard, so that we could compare directly with other methods that are proposed in the literature. And the core idea that I proposed in this case to improve the existing models is to incorporate the cyclic processing of the model. So before that, I think that all of the proposed solutions work in a very simple way, where we just have the noisy spectrogram on the input. We provide that to the input to the neural network, and it produces a complex ideal ratio mask, and we remove the background noise. But I proposed to train a model in such a way that is able to process the same input signal multiple times, basically implementing the cyclic, the sequential cyclic processing within neural network. So the schema that I proposed is like all the Fs in here is the same neural network. At the input, we use the same model multiple times, and at each time we provide the exact same noisy speech. But there is something that can be called like a skip connection. When we, at the end of processing, we generate some kind of information and we provide it at the input to the same neural network, the same weights. And this way, the network can look at what it predicted the first time and tries to improve its own output. So basically, the network becomes aware of its own output and tries to do better next time. So this was something new, and in order to do that, I first needed to figure out where this connection should be made within the neural network architecture. And the answer that I found was that we could take features that come into the input to the final convolutional layer of first iteration, and we can add them to the features that come out of the first convolutional layer in the second iteration. And this way, because this contains almost all of the information that the network produced when doing the speech enhancement in one iteration, this information is provided at the input to the second iteration, and then the network can compare like the noisy signal with what it predicted in the first time and try to make a better output. Basically running the same neural network multiple times, making sure that the predictions are consistent, and it removed all the noise as much as possible. Because this is a very general concept, this was tested for different architectures of neural networks. I won't be going too much into details, but we tested three most popular architectures that are used for speech enhancement. And for each one of them, we were trying to apply this, this multi-stage enhancement approach. And these are the results that we got for one of first of the three metrics, STOI, short time objective intelligibility. So the dashed lines over here, these lines represent the performance of the model, the baseline model that was making just one prediction, just one pass through the network and one prediction. And yeah, just to interpret these values, the higher the number, the better, okay? So we are here. And the solid lines over here represent the performance of the model that was trained to do 5 passes, but we tested its output after each pass. So after one pass through the model, 2, 3, and 4, etc. So what's interesting here is that we can see that when we train a model to do 5 passes, but we actually do only 1 pass, the performance is slightly lower than the baseline model. So in other words, we had to sacrifice a little bit of the performance of the model to learn it, to be able to improve itself. There is some little cost that we had to pay in order for the model to be able to do that. But as we can see, when the model already performs two passes, we already see a very clear improvement over the baseline. So we sacrifice a little bit performance when we do 1 pass, but when we do 2 passes or more, the performance is getting much, much better. Of course, it saturates at some point. It cannot grow indefinitely. So there is some limit here. But there's definitely like progress in how well we can suppress the background noise just by repeating this analysis and being able, making the network able to self-improve itself, okay? The same patterns can be observed for other parameters. PESQ shows a similar pattern, and SESDR, scale invariant signal to distortion ratio, also shows a very similar pattern of improvement. Although one thing interesting can be observed here is that this architecture, residual bidirectional LSTM, shows the smallest improvement. And this fact should be connected to the fact that this architecture contains the most neurons. This is by far the biggest of the 3 models. And this is also a very interesting observation. Okay, an example. At the top, we have a noisy signal that we provide on the input to the model. And we have spectrograms after each iteration of the model. At the very bottom, we have what is called our ground truth, so the clean speech signal. And on the right over here, we can see the amount of noise that was removed at each iteration. And yeah, the progress between the first iteration and the 5th can be quite clearly seen. And especially, I like this sound that appears at the very beginning here, because you can clearly see that after first pass, the network is still not sure whether it's a speech or not. It basically left this sound almost intact. But after 2 or more iterations, it actually learned or figured out that this is not part of the speech. It was able to recognize the tone of the voice of the speaker, and this sound didn't match. So eventually, after 2, 3, and more passes, it became more and more certain that this doesn't belong to the speaker, and removed the sound almost entirely from the recording. Okay, so eventually this project was quite successful. We could show that each of the 3 architectures that we considered were able to self-improve themselves by multiple iterations. The transformer network and UNet benefited more from multiple pass enhancement, probably because they had the fewest fewest neurons in their architectures. So I conclude that they are able to better reuse the neurons, the very limited number of neurons that they have. And it's like a little bit like a virtual way of virtually increasing the number of neurons in a network, even though it's very small. Again, this approach has a disadvantage. Computational complexity scales linearly with the number of passes, which means that Of course, we need to pass the same signal multiple times through the network, so there's additional computational complexity involved with each iteration. Although this also gives a very interesting opportunity, because if we design the network that way, we can now say that we can dynamically adjust the number of passes depending on the number of available resources. If the resources are very scarce, we can do just one pass and already have a decently denoised signal. But if we have more resources, we can keep on repeating the cycles and have a better quality signal. So this gives a very natural and probably very useful feature of this kind of model. I also noted that this is probably a very similar approach to what modern large language models are using right now. You probably noticed, if you are using large language models, that the current generations are models that are thinking deeply about the problem. And usually they are doing this in many steps. You can sometimes even see the intermediate steps of what the model is thinking, and then it's rethinking that, et cetera, et cetera. So this is a very similar approach, but in here, this is applied specifically for the audio processing problem, let's say. Okay, to wrap up my presentation, 3 conclusions that I prepared for you. As the performance of artificial neural networks saturates, further advances can be achieved by drawing inspiration from neurobiology and high-level human cognition. I think that this is a very potent source of inspiration for further improving the neural networks. I'm still fascinated by the fact that despite the fact that artificial neural networks are so very simple approximations of real nerve cells, the artificial neural networks show remarkable resemblance to how the brain works. And usually things that work, or we know how they work in the brain, they also work in artificial neural networks. And this is quite fascinating to me. And yeah, I think that this line of research shows that if we allow the models to think more like humans, to think multiple times about the problem, or look at the problem from multiple perspectives, this is a very valid way to improve the accuracy and performance of the models. And I expect that this is something that will be further advanced with follow-up research in next years. This is all from my side. Thank you for your attention. And if you want to contact me, there are some contact details on the slide. Thank you.
Thank you for a very interesting presentation. Now we have time for questions, comments.
Yes, so thank you for the very interesting presentation. So I have the question regarding this
pre-training.
Yes, and exactly freezing of the layers. So my first question is, how do you choose which layers to freeze? Do you freeze like first n of the layers, or by random, or you pick specific layers? And this is with connection to the other one, because I would expect some peak at the number of chosen layers, whereas we have like flat plateau at the beginning. So basically what it shows that there is not much difference between freezing 1 and 4 layers. So my question is, what is the reason for that? Because I would expect that freezing some of them would be most beneficial.
Yes, that's a very good question. So the practice of machine learning is that we usually freeze initial layers. So we usually decide how many layers from the beginning of the network we should freeze. I've seen questions asked and answered before, like, wouldn't it make sense to freeze layers in the middle of the network? And this usually doesn't work, because we start from those very general features, and then there is usually a place where is the optimum, as you said. And so yeah, definitely we start from the beginning, and we usually decide how many layers should be frozen. I was also quite surprised that this is so flat, but actually when you look at the numbers, there is a very small advantage of freezing 4 layers instead of like 0 layers, but it's probably insignificant. My suspicion is that because we had very different types of sounds, and some of them were very, well, for some of them, freezing 0 layers was better, and for some of them, freezing 4 layers was better. So there was, like, in this area, there was always a trade-off. Some of them were better, some of them were worse. When we were here, it was much easier to detect short peeps because we need very specialized features to detect them. But when we were freezing these, we were already much better at detecting distress calls because we already had the features required to detect these sounds. So I think that in this area, we had this trade-off between what kind of sounds, what kind of features do we have, what kind of sounds are we want to detect, and this plateau, exactly the fact that we had plateau over here, inspired me to build this branch model so that I don't have to make the decision like this, because obviously each of those models works in a slightly different way, but they all have a very similar performance. But underneath, under the hood, they are working differently. So this is why I didn't want to make this choice, because I knew that there is something I could gain if I could leverage all of these at once.
Okay, thank you. The next question.
I'm not sure if I understood that your iterative method, how does it differ from normal backpropagation? Because in normal way, we go through all the layers, and in the end, we have someone tell us, this is good, this is wrong, and we teach the intelligence what's right and how she should correct its weights.
Yes.
And in your method, I understand we stop after first or first 3 layers. And where is that new knowledge coming from? Because we didn't get to the end. There is no teacher which tells you what's wrong.
Okay, thank you. I will try to explain this one more time. So in here, this F function, it doesn't represent a single layer. It represents a whole neural network. And this output here is a complex ideal ratio max, so the output from the whole model. So, you could say that this here only shows the inference part. So we have the same neural network, whole network. It has multiple layers and has an output. And we use that model multiple times. And we have multiple, it makes multiple predictions, okay? So we have an input signal, we provide it at the input to the model, it produces a complex ideal ratio mask. So we have an output from the model. But it also produces this information, which is very highly related to this one, and then we use the same model again. The whole neural network is used again. We again provide the noisy signal over here. This information that was extracted that is highly related to this output, and now the model has these two information and can make a second prediction. So the difference is that one model produces multiple outputs, not by the fact that it has different layers, but the fact that we provide, make passes through the whole network multiple times. And so when we are training this model, okay, assuming that this is repeated 5 times, the whole schema produces 5 outputs. Each one of them is a complex ideal ratio mask. And the way that I was training this model is that on each output, there was a loss function. In here, I was calculating a loss function between the output from the model, the predicted complex ideal ratio mask, and the ground truth complex ideal ratio mask. And then this was averaged. So the network was trained to provide the best approximation possible after 1 iteration, 2 iterations, 3 iterations, 4 and 5 iterations. So this is not how a typical neural network is trained at all. Usually we have only this. We have an input, we provide it to the neural network, and we have an output. And in here, we have a loss function. So it produces a complex ideal ratio mask, we compare it to the ground truth complex ideal ratio mask, and then we back-propagate the information and upgrade this model accordingly. And in here, instead of one output, I have 5 outputs. Each one of them was trying to make the best prediction possible. Each one had a separate loss function, but the actual loss function that was used to train this multi-iteration schema was an average of the losses on all 5 outputs. This is shown in here. So it might be slightly confusing because this is the input. We have a noisy spectrogram, and this is actually shown for unit. Okay, so we have an input. There's a first convolutional layer. So we have first layer of neurons, and we have some features over here. Over here, we have a huge network. It consists of multiple layers. It produces all the information. And then we have an output convolutional layer, which produces, well, this might be slightly misleading. It doesn't actually produce a sound. It produces a complex ideal ratio mask that is used to obtain this kind of sound. So when we are doing the first iteration, in here we provide only zeros. So because here is an addition, it doesn't change those features. The features that come out of this layer are provided at the input here, and this is 0, so nothing changes. But in here, we take features that come out of this next to last convolutional layers. We have them in here, and then we provide the same input signal, but this time we are adding these features to the features that come out of the first convolutional layer. And after this operation, this is a combined knowledge about the input signal and what was predicted in the previous iteration. So this can be thought of as a huge recurrent step that incorporates the whole neural network. Usually when we have recurrent layers within the network, we iterate over one feature map. So for example, we have a feature map, and we iterate, process, for example, time steps or frequency bands in a recurrent way. In here, we enclose the whole neural network within a recurrent step, and therefore it produces multiple outputs. What's unexpected is that the actual input is exactly the same in each iteration. But this is done on purpose because we need to make sure that each consecutive iteration will not degrade the signal. That's why we provide the original noisy signal at input to each iteration. Usually, when we would do a classical recurrent neural network, the output from one iteration would be provided at the input to the other one, but we will no longer have the information about the original input. In here, I had to do that because otherwise, each additional step would remove more noise, but it will also degrade the speech. But because I'm doing that, the speech will not be degraded. We will be only removing more and more noise.
Okay, next question.
Thanks for a nice talk. In general, when we perform simulations, we have to build a baseline of our system, then we perform the rest experiment while simulation. So in your case, you build the artificial neuronal sets, a network. How did you make sure they are communicating very well before your experiment?
Could you repeat the question?
Before your experiment, how did you make sure your artificial neurons are connecting 100% correctly like they connect in our brain?
If I understand your question correctly, of course, the performance of this multi-iteration model was compared to the performance of this model. And to be honest, this kind of architecture was designed specifically in such a way that introduction of multi-pass enhancement didn't create any additional parameters. If you look at this, if we provide zeros over here, this addition doesn't do anything, and we have our baseline model that does one pass. And when we introduce multiple passes, we don't even add a single neuron. So this was quite important for me because it makes the argument a lot more easier. I can show baseline model that has exactly the same number of neurons and measure its performance, and then have my multi-pass model and also measure its performance. And nobody can argue that the performance of the multi-pass model is better just because I added neurons, because I didn't add any neurons. This is like, from the point of view of architecture, they are identical. The only difference is that we are adding this arithmetical operations here. So this is, if I understand your question correctly, this is how I ensured that the improvements that I am trying to show, they only come from using this method and not from fiddling with the architecture itself.
So how many models did you use?
How many models? We tested this, as I said, for 3 different architectures. So we used transformer network, residual bidirectional LSTM, and dilated UNet. In the paper, we shown one version of each of those, but of course, in the experimental phase, we were also checking different configurations of transformers, LSTMs, and UNets. But they have all shown a very similar pattern that I've seen here. So we were trying to show the general approach, and that the approach is valid independent of the actual architecture of the model.
Actually, if you study neurons, the main problem is that you must have to study electric potential of the neurons and diffusion in our brain. So I am confused, which model should we consider to study this thing, because I have research on this thing.
Well, this is all these models are built on a like standard definition of a neuron. I didn't talk about this in detail, but in terms of like the architecture on how the neuron works, it's completely standard. It's like weighted sum of the neurons connected from the previous layer and the nonlinearity over here.
Okay.
So yeah, this is like the most basic. I'm not sure if in all research we use actually ReLU. This is just for example. I think we probably used ELU instead of ReLU for nonlinearity in here. But like the definition of a neural network is as standard, as simple as in any other artificial neural network research.
Okay, thank you, sir.
Okay, thank you. Next question, yes.
I'm just curious. Does this neural network allow us to predict whether a chicken is sick before any human vet could say that based on symptoms? Can we somehow speed up the treatment or something? And does it work for other animals also?
That's a great question, but unfortunately, I don't know the answer to that. I think the research is still in infancy, let's say. So I don't think we compared the performance of our model to a performance of a veterinary expert. Just from my knowledge of how the poultry works, I think that because it's like the veterinary oversight, it's not continuous. From what I remember, they usually check up in the big stables that they have in Belgium. They usually check up on them like once a week, maybe. So from this point of view, I'm absolutely sure that using the method that I'm showing, we are able to detect that sooner. But if we just have a veterinary with his headphones listen to chickens and AI, I don't know who will be faster to detect the abnormality. I don't think we are at this point to make this kind of comparisons. But just like from the point of view of the processes that are happening in the stable, I think that what we already have is a big step forward for the poultry industry.
Okay, thank you.
Thank you. Oh, yes, question.
Thank you for the talk. If we could see the comparison between the In the section with speech processing, this comparison between the three models. Yes, so this on the y-axis, this number is, I guess, the. Could you explain what this number means?
Yes, so this is short time objective intelligibility. So this is a standard metric that could be interpreted as a percentage of correctly recognized words. Okay.
Okay. So from this plot, we see that that your approach it's enhanced by a few percent. Can this be? If you played a denoised sample with just this baseline standard model, let's say, compared to your model after a few passes, can a human ear actually tell that that one or the other is less noisy?
Yes, that's a very good question. And to be honest, we haven't done that kind of comparison. We wanted to do that, but eventually we weren't able to do that yet. I think that just by looking, well, I don't have the numbers in my head, but I was also asked, I think, by one of the members of the examination committee for my PhD. I was asked about that, and I checked the literature, what they say about what kind of percentage differences is actually subjectively detectable, and I think that these kind of differences should be detected by an average person. Let's say they should hear the difference, and it should be audible to them. But to be honest, we haven't measured that in real humans. I think. Well, we didn't do that. I don't think. I'm sure we didn't do that.
Okay.
I just well. I only have the numbers, so I think that.
But subjectively, did you play the two, let's say, recordings, and did you hear differences?
Oh yes, definitely. Yeah, we did that, and the difference was quite clear. Although for me, like I wasn't 100% sure if it actually improved my intelligibility of the sound. I was certain that I hear a lot less background noise. But I'm not sure if this difference in the background translated to me better understanding the actual speech.
Okay.
Yeah, but absolutely, I'm absolutely sure that the difference in what is in the background is audible because I tested it myself and I could hear that without a doubt.
Okay, thank you. Okay, it's close to 2 p.m., so I think we have time for one last question.
Well, this is just short comment to that, because I imagine that if you're using like this device for very long periods of time, then there's less noise. Even if it doesn't improve readability of the words, it's more convenient to use.
Yes, probably less tiring, and over a long period of time, it might be less fatigue for you, and you might be able, for example, to work longer without being tired. Yeah,
so
that's definitely.
Okay, the last question, short. Oh yes, probably comments.
So as a co-supervisor of your PhD, it's just a comment that all my scientific life I work with kind of these things. Like speech improvement, and we must think of it that we are doing it for humans. So at the end, speech intelligibility is one thing, but acceptance of this new signal that is denoised is the other thing. And sometimes it happens in some algorithms, especially classical, that speech enhancement is very high in speech intelligibility, but then people who use this technology cannot stand the sound as it is, because it is distorted in a way that they understand, but it's not natural at all. So the question is, after this processing, does it sound still natural or not?
Yes. So I would just refrain what I already said. This is one of the reasons that for me it was very important to have this model where I'm doing multiple iterations, but each iteration receives the original noisy signal, so that this model is able to keep the original speech and not add additional distortion to the speech itself. And I think that this is one of the most important aspects of this model. That is better than, for example, approach that is called progressive speech enhancement, because there is something like progressive speech enhancement, but it works in a different way. We have like cascade of neural networks, and each of them is trying to remove some of the background, like for example, 10 decibels of the background. And this is different than my approach in a couple of ways. But one of the ways is that is like in my case, each iteration works on an original noisy signal. So it tries to remove more and more noise, but it keeps the speech intact. That was the idea and the motivation for this kind of architecture.
Okay, thank you. Thank you, the speaker again.
Thank you.
And I invite you to the next seminar in the next week. Thank you.
Tak? Jasne.